Alright, in this video we're going to be talking on oxymecuration-demecuration of alkenes. And this is also alcohol formation. It's a method of forming alcohol. So that's why I just put alcohol formation at the bottom of it. So let's get started. Now this is a type of reaction alkenes undergo which leads to the formation of alcohols, like I said earlier. It involves the use of water and mercury acetate in a reaction called oxymecuration. Then after this, a reducing agent such as sodium tetrahydroborate is used to reduce the product of the oxymecuration reaction in a reaction called demecuration. And there's something we need to note about this. Oxymecuration-demecuration of alkanes give a better yield of alcohol compared to the addition of water in the presence of H2SO4. I am sure you guys have heard of that reaction. Like the normal reaction of alkanes to form alcohol is the addition of water in the presence of H2SO4. H2SO4 acts as a catalyst and help in the dissociation of water into hydrogen ion and hydroxide ion, and they end up pairing with the alkanes and forming an alcohol. But this reaction, this oxymecuration-demecuration reaction that we're actually looking at right now, gives better yield of alcohol than the previous reaction that we just talked about. So like industrially, this reaction is better. That's just something that we need to note. Now I'm actually going to be talking about the mechanism of this reaction right now. Now the first thing that we need to know is that in the presence, like in a solution, what actually happens to the mercury acetate is that it dissociates into its respective ions, and we are going to have something like this. So in this example, I'm going to be using ethanoic acid, like mercury salt of ethanoic acid. That's what I'm actually going to be using to do my example. So it's not going to be really complex or confusing. So let's just go with it. So we have HgCH3COO2. Now the first thing, like I said, is the dissociation of this into its respective ions. That is its positive ion and its negative ion. And we're actually going to have this. This is anion and this is the cation. Now this is the two ions that we're actually going to be dissociating them into. But in the case of this alkene formation, this ion play no part or play no role. Actually, the role can be seen later on, but it plays no role in like the formation of the alcohol. So we're actually considering this ion because we are actually like the pi bond is the mobile bond and is the bond that we want to donate, and we see that the ethanoic ion is actually rich, electron rich, but the next ion, that is the salt of the ethanoic ion, the mercury salt of the ethanoic ion, is actually electron deficient. So it's actually the one that is better off for bonding. So let's continue with this. Now, like I said earlier, we're actually going to only be using the cation in this case. So let's just go on. Now we have this an alkane. This is an alkane. Depending on the arrow can represent anything in this case. Now the first things first, like I said, this ion, that is the salt, mercury salt. Let me just call it mercury salt for now. Now the mercury salt will actually attack the pi bond electrophilically. That is electron deficient, and we all know electrophiles, they actually attack and they're looking for electrons. They're always looking for electrons. So it actually attacks the pi electron and forms a bond with either one of the carbons. Since we're actually looking at a double carbon, we can actually form with either one of the carbons. So let's actually go and see this is what is going to be formed, R2. Then we have something like this. Now, if we notice something, Notice something. Carbon, let me label the carbon so we won't have problem when I'm saying carbon number 1 and carbon number 2. Now we notice something. Carbon number 1 is tetravalent, like that's like a normal, all its bonding pairs, they are all like connected, so it is stable if I put it that way. But carbon number 2 is deficient, and therefore it has a positive charge and becomes a carbocation for the first part of this reaction. So just note this is like the intermediate form. Now another thing that I want you to note is what I'm actually going to be correcting here. Please note this is very important. Now this mercury salts won't actually just form an intermediate with this complex at once. It's actually form a cyclic intermediate, if I put it that way, or a bridged intermediate. That is, the double bond or the pi bond will actually be resonating between the carbon number 2 and the mercury salts. That's actually what's going to be happening. So it will keep resonating, and that will partially make this carbon number 2 stable because of the resonance effect. Partially make it stable for now. Then the next thing is that, let's erase the board, and then in the presence of water, this is what we had before. In the presence of water, another intermediate is actually going to be formed. Now this resonance form, that, like I said earlier, won't be needed again, because now the carbon number 2, that's the carbocation, is actually accepting electrons, so this intermediate is not going to be formed. Now we all know that water is a Lewis base, and Lewis base are electron pair donor. Even if what's actually going to be happening, we all know the structure of water to be something like this, and has 4 lone pairs of electrons. So actually 2 of these lone pairs is actually what's going to pair with this carbocation and actually going to form a bond with it. But note something, water won't dissociate. Water only dissociates in the presence of an acid, and not just any acid. Yeah, in presence of an acid. That's the definition, Arrhenius' definition of an acid. They both dissociate in the presence. So just note that water will dissociate in only the presence of an acid. Now there's no acid present in this reaction, so water is not going to dissociate. Instead, it's going to combine as this group. Like I said, it is a Lewis base, so it already has lone pairs of electrons, so it can actually just donate those lone pairs of electrons, and they actually form bonding pairs. So it's not actually going to take anything away from it. So let's continue. So what's actually going to be formed now is this intermediate. So we have this intermediate. Now the resonance bond can actually relax and go. Then we have something like this formed. Let me take it up because there's no space at the bottom, but it's still the same thing. So the oxygen pairs here and the water pairs as a whole. We can still put our 2 lone pairs of electron because there were 4 lone pairs. Now we can still include our 2 lone pairs of electron. So now this is actually what's going to be formed. This actually was going to be formed at first. So the next step that I'm actually going to be talking about now is that the oxygen that we can see now, this oxygen here, oxygen normally it's meant to like accept 2 electrons and actually become stable, attain its octet structure. But if you can see from here, oxygen now has 4, like it has 4 pairs. Like if I put it this way, 1 2 3 4 5 6 7 8. Now it's pairing with both carbon and 2 hydrogen. Instead of it to be pairing with 2, it's actually pairing with 3. Just take that, it's actually pairing with 3. So oxygen is actually having, like, it's electron deficient, if I put it this way, or no, electron rich. That would be better for it. It's going to be electron rich, and that's not good for oxygen. So what oxygen is actually going to do is going to donate, or what should I say, lose this hydrogen completely. So this hydrogen ends up being eliminated. So hydrogen ends up being eliminated, and then the charge of that hydrogen, the hydrogen ends up being eliminated as hydrogen ion, and then the charge ends up becoming here, and that's like it's hydroxide ion and so on. So at the end of the day, we end up that we find ourselves with this intermediate. Yeah, we find ourselves with this intermediate hydroxide ion, and that's like partially consistent with what we're actually looking for, because after this we know that we're actually going for our demecuraton reaction. Now, like I said earlier, then after this, a reducing agent such as sodium tetrahydroborate 3, that is the agent we're actually going to be using for our demecuraton reaction, and that's the next step that's actually meant to happen. So we can see that this is stepwise process. Now let me just tell you something I need to know. Whenever an organic compound is combining with a polar solvent, the reaction is stepwise, but whenever it's combining with a non-polar solvent, it's a one-step reaction. Just know that in case you're doing any stuff and you're asking, is there an intermediate formed? If an intermediate is formed, just look at the substances combining with, or the compound or element is combining with. If it's polar, just know that there's an intermediate form, but if it's non-polar, there's no intermediate form. Both reaction occurs at once. So just know that. Now you can see that this is stepwise reaction. So the third step, actually, like I said, is the formation, like it's combining with the reducing agent now. So we actually we're having something like this. Now the reducing agent, like I said, sodium tetrahydroborate 3. Now we have this. Now it's actually going to be combining with. Now we need to advise. Yeah, we need to note this also. The reducing agent needs to be mild. We don't need a strong reducing agent like lithium tetrahydroborate 3 or lithium tetrahydroaluminate 3. We don't need that type of reducing agent. That's the really strong reducing agent. That will end up destroying the entire structure we're actually looking for, and maybe even lead to the formation of an alkane. And that's not what we're looking for. We're looking for a function of alcohol of an alcohol. So we need a mild reducing agent such as sodium borate. So that's what we're actually going to be using now. And then look at what's actually going to happen. A hydrogen from the sodium tetrahydroborate will actually come and displace this mercury salt. This mercury salt is a good leaving group, so it's actually just going to leave with no problem. So let me just write this: good leaving group. A good leaving group. So this actually what's happening. The mercury acetate is a good leaving group, so it actually leaves, and then the hydrogen comes and fill in this space. And at the end of the day, we end up that we have an alcohol. An alcohol is formed, and this is the product we're actually looking for. So the reaction is actually complete. But now I just want to talk about what happens to the mercury salts. So let's talk about what happened to the mercury salts. Now, still the same thing. Like, what's going to happen to the mercury salt? Like I said, is displaced. Now we know we're still in the presence of the reducing agent that we just added. So it's still like ready to attack. So what's actually going to do is actually like a hydrogen from this reducing agent to actually displace the mercury from the mercury salts, and actually going to lead to the formation of an alkanoic acid. Now this ethanoic acid and mercury, this is what's actually going to be formed. Now at the end of the day, we find out that from this oxymecuration-demecuration reaction, that three products are actually going to be formed. The most important one, the alcohol, mercury, and a carboxylic acid. So these are three products that are actually going to be formed. And that's all for oxymecuration-demecuration reaction. So thank you for watching. Please like and subscribe to my channel. Thank you.